Hello and welcome to this lecture on series. In this lecture, I'm going to tell you about the concept related to series. We will see different type of series, but before starting this lecture, it is recommended and must that you should be clear with the concept of sequences. I will highly recommend you to see my previous video on sequences to clarify your concept relevant to sequence. So let's start this lecture by seeing the definition of series. If the terms of sequence are added, the result is known as a series. For example, if we add the terms of the sequence 2, 4, 6, 10, we obtain the series. Clearly, a series is a sum. If the series contains finite numbers of terms, we are able to add them all up and obtain the sum of series. If the series contains an infinite number of terms, the situation is more complicated. An infinite series may have finite numbers, in which case it is said to be converge. Alternately, if not, then it is diverge. So let's see how we can label the sum of series. A sigma notation provides us a concise and convenient way of writing long sums. It is a Greek letter which is sigma and it is used to represent the sum of values. So let's see the example. The sigma stand for sum. In this case, the sum of all the values of n ranges from the whole number from 1 to n. Note that the lowermost number is the lower limit and the uppermost number is the upper limit. Okay, and we will plug in all these values in in place of n, and we will get like n is equal to 6. Okay, we'll get 12 because we are putting n is equal to 2. We'll get 18 if you put n is equal to 3, and we'll get 4 into 6, 18 if we put n is equal to 3, and if you put n is equal to 4 and 6. So if you put n is equal to 3 and you put this in an equation, and you will get 18. If you will insert n is equal to 4, okay, in this expression we will get 24 and so on, like 30 and 36. So let's see another example where we need to convert the expression into sigma notation. So we have 2, 4, 6, 8, 10 plus 12, the given expression, and we need to convert it into sigma notation. So how will we do that? So we know that the lower limit is 1 because 2 is at position number 1, and the upper limit is 6 because 12 is at position number 6. So we can easily plug in the value of n is equal to 1 up till 6, and we can easily see the pattern between these numbers. Like we can see that 2, 4, 8, 6, the next number is 4, the next number is 6, which is if we add 2 in previous number we are getting the next number. So we can make expression 2 into n to get this expression. So let's see another example. So in this example we need to find the values by plugging in the values of n from 0 to 3. So if you insert the value of n is equal to 0 in this equation, you will get 1. If you put the value of n is equal to 1, 2, definitely we'll get 2, 3, and 4. So let's see different types of series. The first one is arithmetic series. Arithmetic series is formed by adding the terms of arithmetic sequence or progression. We have covered this arithmetic sequence and progression in our previous lecture. If you want to understand about the arithmetic progression or sequence, I would recommend you to see my previous video on sequences. So general notation for this arithmetic series is Sn is equal to n divided by 2 into 2a plus n minus 1 into d. So whereas a is the first term and the d is the common difference between two terms. So let's see some example to clarify the concept. First example, find the sum of first six terms with common difference 2 and the first term is 3. So A in this case is 3 and D is a common difference which is 2. We'll insert these values into this expression and by computing all these expression we will get 42, which is sixth term in the arithmetic series. So let's see another series which is geometric series. If the term of geometric sequence, also known as geometric progression, are added together, it will result in geometric series. The general notation for geometric series is given as Sn is equal to A into 1 minus r power n divided by 1 minus r, whereas A is the first term in the sequence and r is the common ratio. Bear in mind that we will not take r is equal to 1. Why? Because if we will take it 1, the denominator will become 0 and it leads to infinity. So let's see some example to understand about the geometric series. Find the sum of first four terms of geometric series whose first term is 1 and the common ratio is 5. So A in this case is 1, okay, and R, which is common ratio, is 5. We will take these values and insert it into this expression, which is general notation of geometric series, and we will compute all these expression and we'll get S4 is equal to 156, which is the fourth term of the geometric series. So let's see the last series, which is infinite geometric series. The term of infinite sequence are added together to get this series. The general notation for this series is given by S approaches to infinity is equal to A divided by minus 1 minus R, whereas A is again the first term and R is a common ratio. Bear in mind that we will not take R greater than 1 and R minus less than minus 1. The series does not converge. Let's see some examples. Example number 1, find the sum of infinite geometric series with first term 2 and the common ratio is 1 by 2. So we will put these values in this general notation of infinite geometric series. A is 2, R, which is common ratio, is 1 by 2. Okay, we insert these values into the expression, which is general expression for the infinite geometric series. We will get S approaches to infinity is equal to 2. So that's it. I hope you have enjoyed the lecture. So thank you very much for listening to the lecture. Lastly, if you want to understand the concept of discrete math, computational math, or if you're interested in knowing more about cybersecurity domain and malware analysis, just subscribe my channel because in near future I'm making more videos on these topics. And if you want to keep yourself updated with these uh, domains, just click on the bell icon so you will get notification whenever I will make new video. I hope you have enjoyed this video. Thank you very much.